So my name is Gunnar Gunnarsson. I'm working at the Reykjavik Energy OR, Research and Innovation. And well, my colleague Vala outsourced this task to me to do this talk, and now working as a project manager of the IDDP3. And the title of the talk is IDDP3, Reaching into the Resource Below. And my colleague Guðmundur Ómar gave you a good overview of the history of the IDDP project. And this project was funded by the three main power companies in Iceland. And the idea was that each company should drill in its field a deep well. And there have been a lot of organizations both in Iceland and internationally participating in this project. And as Guðmundur Ómar told you, the first well was drilled in Krafla and drilled into magma at a depth of around 2.1 kilometers. It's a very interesting well and interesting flow tests. However, as you heard, the casing was damaged when the well had to be cooled down, and it had to be closed with cement, this well. And the second well drilled in Reykjanes down to about 4.6 kilometers. And there we really measured, we got this measurements, direct measurements of supercritical condition, 426 degrees Celsius and 340 bars. And however, the casing is also damaged in that well, and the lower part of the well can't be reached. And now we are planning the next well, the IDDP3 in the Hengill area. So if you just take a look at schematics of a typical geothermal system in the Icelandic rift zone, as we have in Hengill and Krafla and also in Reykjanes. We have this, the rifts, fractures providing the permeability. We have some heat sources in the form of magma or intrusions below, and a lot of water in form of precipitation and or seawater in Iceland. And in the conventional production, we are really only scratching the surface of this. And we can assume that we have a lot of energy below our systems. So a lot of hot cubic kilometers that we, well, we want to know. First, we of course want to know, we are curious, how does this system work? And we want to get this energy, and we want also to figure out how to produce this energy in an economically sound way. So there are a few challenges that we need to tackle before we can really in drilling and operating a superhot well, and we have gathered a lot of experience in the previous wells, as Guðmundur Ómar told you about. And now we have to take the lessons learned and plan for the next well. And first is we need to know and understand the heat sources and their interaction with the water, and understand our system. And Amanda Volker was talking about the Deepen project. That's part of this effort of trying to locate interesting formations to drill into and understand them. Then I think the biggest challenge is the well design or well integrity, because we have this extreme thermal expansions due to inducing very high stresses, and also cementing the casing is something that is very important to do it correctly. And then there's also a challenging chemistry of the produced fluid, mainly HCl, hydrochloric acid, and also silica or silica scaling. And now we're going to talk a little bit about the understanding and the heat sources and the heat sources. And well, we have a lot of hypotheses on how this works, and what we need to know a little bit more of the size, shape, and depth of the heat sources, and how this really works, the heat transfer and the heat budget of the systems. We saw here earlier today some very interesting modeling work from the Zurich group. And yeah, we'll also understand how the depth range of the water convection and the brittle ductile boundary, where it all lies. And what we have seen in few instances in Iceland, there are very hot or shallow heat sources, like in well NJ11 in Nesjavellir, and of course the IDDP1 well in Krafla, and more wells there. So the area that we are going to work on is the Hengill area, and here you can see a map of the Hengill area showing the formation temperature there at 1,000 meters depth below sea level, and 1,500 meters depth below sea level. And this in the southern part is the Hellisheiði field. The blue lines here are the directionally drilled wells. And here is the Nesjavellir field. And you can see this hot formations, and yeah, well, we are going to take a look at a cross section through the system from the south to the north. Here is the Hellisheiði field, and here is the Nesjavellir field. And the formation temperature is characterized by really narrow hot areas and with cooler areas in between. We also have seen variations in fluid chemistry indicating compartmentalized reservoir. So what things that we have here are shallow heat sources and or variations, very strong variations in permeability. And well, the interesting formations are probably relatively small. And what is interesting here is this here area in Nesjavellir. And this is the temperature that was measured in well number NJ11 in Nesjavellir. This is the well really that sparked or started this IDDP idea. Mighty well NJ11. It was unexpectedly drilled into very hot formations in 1985. Formation was more than 380 degrees at the depth of around 2,000 meters. This well was a relatively short production casing, around 565 meters. And there were a few feed zones just below the production casing, and there was a flow from deep feed zones up to these very shallow feed zones. So we had really a underground blowout, and the drilling string had to be pulled out of the well, and the bottom part was sealed off. And these here are the only temperature measurements that are available from the well. This was done with a relatively primitive measuring instruments, clock-driven instruments, and we have here the 380 degrees in the bottom part of the well, but that was the measurement range of the instrument. And since that, there was like a commandment, thou shalt not drill deeper than 2,000 meter in Nesjavellir, and we have until recently just obeyed this law. So as I mentioned, this well sparked the idea of the drilling project. So, and I think there is this initial interpretation of the NJ11 data assumed that supercritical point, that is more than 373 and higher pressure than 220 bars had been reached. However, as I mentioned, the data from this well is very limited. So, well, temperature was indeed very high. However, there are no direct pressure measurements available from the well, and the bottom hole pressure was just estimated. However, the idea of drilling deeper was born, and so we wanted to try to drill a well that could yield supercritical fluid with energy density like more than 3,000 kilojoules per kilogram. And yeah, the aim was to drill into the hot formation of NJ11 and be prepared So this is like the primary goal of IDDP 3. I think we will go for the NJ or this Nesjavellir formation. However, there are other interesting formations in the Hengill area, and there is one here. Here is the Nesjavellir where the NG11 is, but there is also some interesting measurements here from Hverahlíð. And this here is the temperature in the NG11, as I showed you before. And we have had here some interesting measurements in a well in Hverahlíð, where we have here over 340 degrees in around 1900 meters depth. So in order to drill this well, and as also Guðmundur Ómar mentioned, we need to ensure the well integrity. There are extreme thermal expansion in long casings and extreme stresses. This can, however, be overcome. So the problem is that the casing expands during the recovery, and the material reaches the yield point, and everything deforms. And what happens when the well has to be cooled down? The already deformed casing contracts and it can fail. And this is even a bigger problem with long casings, and when you have higher temperature differences, so this will be more likely to fail. However, there is a recently available solution to this, that is so-called flexible coupling. Coupling that will take in these thermal expansions, and I'm pretty optimistic that with some suitable cementing solutions, we will be able to mitigate these stresses and really ensure this mechanical well integrity. So we have, as I mentioned, there was this ban on drilling deeper than 2,000 meters in Nesjavellir, but we recently broke that ban. So this is a map showing where the old NG11 is, and this is the drilling path of the newest well in Nesjavellir, NG32. And we drilled it from the eastern part of the field into this hot area. We revisited the data from NG11, and we thought that the pressure was most probably overestimated, so we decided that it was safe to go for this well. And we tested we had one of these flexible couplings in the well. Decided to test this new technology in as well. And we had a relatively long production casing, and we got very interesting results from this well. Here you can see temperature and pressure measurements during pumping tests when the well completion program, and you can see here the temperature for different pumping rates from 26 liters up to 100 liters per second. And what is very interesting is that we get the highest measured temperature in the well at the highest pumping rate. And this can be understood if we take a look at the pressure measurements that were done simultaneously. You can see that as the pressure rises with increasing pumping rate, also the temperature in the lowest part of the well rises, and just matches the boiling point curve. So the water that we pumped onto the well went into the feed zone here around 1600 meters, but did not go all the way into the bottom part of the well. So we had there some over or superheated conditions in the bottom of the well. And this brings us to the next challenge in operating and drilling, or drilling and operating superhot well. That is the chemistry of the fluid. And what we saw when we were measuring this well, we got the instruments. They came like this out of the well. So we really encountered a very corrosive environment. To the left here, we had here the measuring instrument of stainless steel, and this instrument came like this, black out of the well. And here we can see a corroded spinner or component of a spinner tool. And this is made of some aluminium alloy. I think it's some aerospace aluminium alloy, and this was really like came out like a cheese. So we have encountered there a very corrosive environment, and we are still working on this data, trying to understand this. So, well, we need to work on these challenges to understand the heat sources, as I mentioned before, and the well integrity. And I am pretty optimistic that we will find some solution. We already have a promising solution for mitigating the stresses, and we have to find out also some good solution in cementing the casing. And also we are working now on a proposal addressing both the cementing and how to mitigate or how to deal with the corrosive environment. And when we have solved this, we can really start to figure out how we want to mine the heat from the depth. And of course, the most interesting scenario is to produce the fluid from the depth if we can get some fluid there. Another solution would be to inject below the system and mine the heat in that way, and let the rocks in between the deep well and the conventional production field take care of the chemistry. And then you can also think of something like doublet to produce or mine the heat from the depth. For example, we could have some other working fluid, as was mentioned here before, CO2 maybe. That's more like a future music. So this brings me to the conclusion. We have really a beast down there, and we want to tame this beast and get the energy. And the figure here is a statue of a wise man from the 11th, 12th century in Iceland, Sigmundur Sigfússon the Wise. He was able to tame the beast and use the devil to ride the devil as a seal over the ocean to Iceland, and used his wisdom to do that. And so we are planning the IDDP3 in Ísafjörður, most probably, as I mentioned, maybe in Hveralíð, but I guess we will end in Ísafjörður. The formation, we need to finish this deepen project to have a better understanding on the formation, and also get a good technical solutions to technical challenges. And then we need, as Sigmundur Sigfússon the Wise, to beat the beast with our knowledge and skills, and mine the heat from below the system. So that was all. Thank you for your attention.
Thank you. Excellent. I really love that last slide. The Taming the Beast is brilliant. I think that could be a logo for the whole session. Thank you. There was one question. Do you think duplex steel material and metallurgy may mitigate the casing issues of large delta temperature and cycling and Euler buckling? I'm not sure what that is.
Euler buckling. Well, I'm not an expert in this field. I have what we think is the most promising solution to this is these flexible couplings. So couplings, casing couplings that can move to mitigate stress in that way. And it's also important, as I understand, to have the well properly cemented.
Yes. Yes, I agree. And there's a question about alloys and materials. What are you looking at for corrosion-resistant drill bits? And I would like to add to that is there any corrosion expert looked at the pitting that you saw in the aluminium or alloy from the logging tool? Is that typical of HCl acidity, or is it stress corrosion pitting? Is there any corrosion specialist looked at that?
Yeah, well, this is most probably HCl, hydrochloric acid.
Yeah.
And yeah, what we are thinking, because we are trying to figure out also how to do this in an economically sound way. And one of the idea is to clad the casing pipe. So we could have a standard material cladded. So
yeah. And I guess another quick question I had was about, do you think that the acidity that's caused this corrosion is related to the mixing of drilling fluids and the supercritical fluids at the bottom of the well? And do you think this might be mitigated with time once the well is produced? In other words, a reduction in the problem?
I'm not sure about that. But this is very strange because we have this corrosion in the bottom part of the well. And that part is more or less, or we think it's almost impermeable, but very hot. So and we had during recovery, we had like a two-phase area between this bottom part and upper part of the well. It was like we were dealing with some kind of distillation there.
Yeah.
It was very difficult to understand this data, and we're still working on that. So we might have had some concentration of some nasty stuff there, and it also temperature measurements during drilling during recovery showed that the changing density in the lowermost part of the well.
Yeah. And another quick question: were the predictions for the temperature at the bottom of the newly drilled well close to what you observed? Did you actually predict the from your extrapolation from the earlier well? Was this more or less what you expected?
Yeah, well, from this well, all the wells that we operate in our fields, and this included the operational temperature is at just boiling point curve or a boiling point. So we are always producing saturated steam or saturated. We have never we've never had overheated steam in our fields in the Hengill area.
Yeah, right. The temperature logs that you showed were during injection. Have you had any heat up logs?
Yeah, we have few heat up logs, and we haven't. And all the temperature. I didn't show it here, but the temperature measurements there were all lower than this because of the lower pressure when we stopped drilling. Stopped injecting, and when the well heated recovered and the water column was hotter.